Hi, welcome back to your new lesson. This is Lakshmi Kanta Tiwari. In this lesson, I'm going to teach you how you can make a CNN for a breast cancer detection. So we'll be having 30 features for each row in a breast cancer dataset. You can go ahead and visit this link here, and this is the original dataset. Although it says that it has total number of attributes 32, in which the first attribute is ID and the last attribute is label. So we can say that there is one label and there is 30 columns for a feature space, and there are total 569 instances are available. So we have two options to download this data. Either we can download this data from here itself in CSV files, data.csv files, and you can see here this data. Okay, so these are the features, like the diagnosis, I mean whether the tissue is malignant or benign, and then we have here the manual features which was extracted from the images of breast, like radius mean, texture mean, perimeter mean, and all other features. And another option we have in which we can directly download this dataset into sklearn, I mean in our working directory. So let's go ahead and switch to a Google Colab notebook. If you don't have Google Colab notebook, you can go ahead and watch my previous videos. I have been working on Google Colab notebooks, and then I have also taught there how you can create a new project. But you can go ahead in a file and then new Python notebook, then you can go ahead and start a new lesson in a Google notebook, Colab notebook. So whenever we start working with the the Colab, we need to first set a GPU type, which you can set from here. Change runtime type. I have been setting a TPU. I have found that TPU is much faster than the GPU. All right. So every time whenever the notebook restarts, we need to install the packages in Google Colab. It's not like our local machine where we need to install just a single time. So here, for every time we need to install a TensorFlow GPU 2.0. This is a current version during this video recording, and it will take a little time to complete its installation. But in meantime, I can explain these codes. So I have imported, once it is installed, then you can import a TensorFlow as a TF, and then you can import a keras from a TensorFlow, and then after that you can import a sequential model from a TensorFlow.keras, and then you can import flattened, dense, dropout, and batch normalization layers from a TensorFlow.keras.layers. And TensorFlow.keras.layers also have a convolutional 1D and the max pooling of 1D. After that, we will not be needing here the image generator. So since I have copied these header files from previous lessons, you can remove that. But we will be also needing optimizers. So we are going to use here SGD, stochastic gradient optimizer, which is also widely known as ADAM optimizer, also known as a stochastic gradient optimizer. And then with this, we can check a version of our TensorFlow, which is currently installed in this Google Colab notebook. And apart from that, we will be also importing some supporting libraries like pandas as a PD, numpy as a NP, seaborn as SNS, matplotlib.pyplot as a PLT, and these are the other supporting libraries. All right. So after that, we will start a step-by-step coding. So it is installing. Just wait for a few seconds before it finishes. All right. So it says that it has installed TensorFlow GPU in my Google Colab. Now you can go ahead and run this next cell, which should print a TensorFlow 2.0, and let's go ahead and run this cell and this cell as well. So we have imported the necessary and the supporting libraries. Let's go ahead and import now a data, a cancer data or a tumor data, which we are going to read into a cancer variable, which we can read from here. You see data sets. I have imported data sets from sklearn as well. So here we have a data set, and then load breast cancer. All right, so here we have a cancer data set. Now we can print a description of a cancer data set by calling cancer and then DSCR. So it will print a description of a cancer data set. It says that, you see here, it says that we have total 30 numeric attributes for a feature, and that's when we can say we have a 30-dimensional feature. And if you want to work on a feature reduction techniques, you can go ahead and visit my channel KGP Talkie. There I have taught so many videos on a feature reductions. Alright, so you can also understand how you can reduce the feature dimensions to increase your accuracy and improve a training time. Alright, but here in this lesson we are not going to do a feature selections, we are going to just implement a CNN. But if you want to do, you can go ahead and first you can make a feature selections and then you can apply your machine learning algorithms. So it has 569 instances, 30 numeric the dimensions for features, and those features are here, like radius, textures, perimeters, area, smoothness, all those things. So here it has 3 categories: the mean, standard errors, and the worst. And you see here it says that about this. So it has mean, standard error, and the worst are largest of these features are computed for each images, resulting in 30 features. Alright, like it has calculated the mean radius, worst radius, as well as, I mean, the worst radius means the maximum radius you can say, and the standard error in a radius. Okay, or you can say a standard deviation kind of. Okay, so mean, standard deviations, and the maximum value has been calculated, and it has resulted to total 30 features. Alright, so let's go ahead and import these data into. Let's go ahead and import this data into Google Colab notebook. So we are going to get the first X in a feature vector, which we can get with the cancer dot the features, okay, cancer dot data actually. And what we are going to do here, we are going to create a the pandas data frame here. So we can do with pd dot data frame, and inside that we are going to pass data is equal to cancer dot data, and then the column name in this data frame we are going to pass here cancer dot feature names. Alright, so with this we get here the X data set, which is the feature space, and with this you can see it has a total 30 columns. Alright, and I'm just printing here first 5 lines. Now let's go ahead and similarly read Y, and in Y what we can do, we can say here we have a cancer dot, and then finally we have here a target. Alright, so let's go ahead and print Y. The Y now says that this, okay, the 0 or 1, and if you want to know what is 0 and what is 1, then you can go ahead and write here a cancer and then target names. So with this target names you can get here, if 0, that's mean cancer is malignant, but if it is 1, then the cancer is benign. Alright, so we have got here X and the Y data, which we will be using to train our model. Alright, so let's go ahead and add first few cells in code cell. After this, what we are going to do, we are going to check the shape of the shape of X variables. Okay, so here the shape of X variable is 569 and the 30 columns. Now we are going to train call a train and test split, so that we can divide the training and the testing data. So in this we have X train and X underscore test, and then here we have Y train and then Y test is equal to a train test split, and in this we are going to pass here X, Y, and the test size, I mean how much data we want to put for a testing, that is 20%, and the random state, it asks about random state, so that we can get the same results as I am getting. Stratify, it says that in a stratify I am gonna set stratify according to Y, so that it can distribute the data symmetrically in testing and the training set. Now let's go ahead and check the shape of X train. We have here 455 and 30 columns, and similarly we can check the shape of the testing data set. There we have 140 rows and 30 column. All right, so with this we have got our the 2-dimensional data, but the neural network, convolutional neural network, accepts a 3-dimensional data. So what we are going to do, we are going to reshape this data. To reshape, what we can do, x train is equal to x underscore train dot reshape, and that reshaping we are going to do for the 455, then 30, and then the comma 1. And similarly we are going to reshape the x test as well, and that we can do x test dot reshape here, and here we have 114, and then here we have comma 30 and comma 1. So with this we have made here, it says that it doesn't have a object attributes reshape, because what happens actually, the data which currently we are having, so the data currently which we are having, it is a pandas data frame. Okay, so in a pandas data frame we cannot apply a reshape. I mean, we can apply reshape on only numpy arrays. So what we are going to do here, we are going to convert it into numpy arrays, as well as we are going to do also standardization as well. Because if you see the X train or the test data set, you will see here the scalings are very much, there are a lot of variance between the features. That's mean all the features are not into a same scale. We need to bring all these features into a same scale. For that we can call standard scaler, so that we can standardize this data, and for that we can do a scaler is equal to standard scaler, and then we can call here x train is equal to scaler dot fit transform, and then here we have x train. And for x test data set we need to just do scalar dot is equal to scalar dot transform instead of fit transform. Alright, so here we need only transform x underscore test. Let's go ahead and run this. Now after this standardization, this data has been pandas data frame has been converted into a numpy array, and in meantime now we can convert this 2-dimensional array into a 3-dimensional array as well. Alright, so we have converted our the 2-dimensional array into a 3-dimensional array. Let's go ahead and build our model. So for building our model, what we need to do, we are going to first define here for how many epochs we want to build our model. So I'm going to say here we want a 50 epochs, and then let's go ahead and get a sequential model. Now with this we have got a sequential model, and then here we are going to add convolutional 1D. Okay, here we are gonna add convolutional 1D with a filter size 32, and kernel size which we are going to set in this is going to be 2, and then activation function, I'm going to set activation function ReLU, and then after that in the first layer of a convolutional neural network we need to provide a input shape, but after that we don't need to provide a input shape, which I'm going to provide a 30 cross 1. Okay, for each input we have a 30 columns and 1 row. Alright, so let's go ahead and add batch normalization. Batch normalization reduces shift variance into a shift into a variance of data while traveling through one layer to another layer. And after that I'm going to call dropout. Let's go ahead and call here a dropout, and I'm going to drop a 20% neurons randomly. After this I'm again going to copy this and just going to paste it here, but if it is not an input layer of the convolutional neural network, then we don't need an input shape, but a filter size here we are going to put it as 64. Alright, and the kernel size is 2, and activation function will be ReLU, but the neuron drop I'm going to put it here 50%. Alright, let's go ahead and copy this, and similarly in fact we are just going to make here 2 layers of convolutional neural network. Then I'm going to call I'm going to flatten this 2-dimensional data into into a vector. That I can do with a flatten. All right, so the model dot add, and then after a flatten we need to provide here a dense layer, and for that dense layer I'm going to put a 64 units into a dense layer, and the activation function for this I'm going to call a ReLU activation function, and after this I am going to call a dropout. Alright, so after this dropout I'm going to call the final output, which is a dense layer, which is 1 actually, the dense one, and then here we have activation function in last, which is actually a sigmoid activation function. Alright, so we have our model here. Let's go ahead and print the summary of this model. So this is a summary of this model. It has around 100,000 parameter, and after this we are going to compile this model. Okay, so we can compile this model by calling here model.compile, and in that I'm going to pass here optimizer, and optimizer is ADAM with a learning rate, very slow learning rate. The learning rate I'm gonna call here 0.005. This is really very slow learning rate, and a loss function for this is gonna be a binary cross entropy. All right, and after this we are going to call the metrics. I mean, we are going to say on which metrics it should evaluate the model. So with this, model has been compiled. Now we are ready to start fitting for this our model. So here we have we are going to record the history of a model training. Now let's go ahead and fit this model with the model.fit, and in that we need to pass here the training data set as well as the testing data set, and along with that we are going to pass here the epochs is equal to, I have already defined this variable epochs, which is equal to 50, and then we can provide a validation split from training data itself. Otherwise we can provide a separate validation data. We are going to use a x test as a validation data. Alright, so here we have x underscore test and y underscore test, and in meantime I'm also going to call here a verbose. A verbose is equal to 1. That's when the training logs should be printed while training. Alright, so let's go ahead and run this cell. It says that the input array should have the same number of samples as a target array. It found that 455 input samples and just 114 target samples. Yeah, so here instead of y test we need to make it y train. Alright, so let's go ahead and run this. So it has started training our model, and it says that the accuracy was started from 75%, but the accuracy has came to around 96 and 97%, which is really very quite good accuracy. But the one thing we need to notice here is that the training accuracy is still 95 and the 96%, but at validation accuracy we are getting a 97%. So that we can say that we can train this model for more number of epochs to increase the accuracy. That's when our model is not overfitting, but it is some kind of in underfitting. Okay, so let's go ahead and see a plot of a learning curve and then understand how our model is underfitting or overfitting. So for this plot, I already have the code written, because in the previous lessons, in all these lessons, so I have been using the same code for a learning curve. You can go ahead and watch these videos, and otherwise you can, the copy you can type it in your the notebook currently. So how it is doing, I'm passing here a history, a training history, and then for how many epochs it is being the train. So it says that it is trained for 50 epochs, and then here I'm plotting accuracy and the validation accuracy. And then in these two lines I'm plotting a loss and validation loss. And if you see here, let's go ahead and run this first. And if you see here a history, all right, so you see this history, have a validation loss and it has here a validation accuracy. All right, it has a loss and accuracy as well. All right, so in this way we can do this. So let's go ahead, we have already run this. Let's go ahead and call this plot learning curve, and in that we need to pass here a history, and along with that we need to also pass epochs, for how many epochs we want to plot the history. So we had trained it for a 50 epochs. Now you can see it very clearly that a validation accuracy is always greater than the training accuracy. That means our model is not overfitting, and the loss of validation loss is also very low, lower than the training loss. So unless and until validation loss goes above than the training loss, we can keep training our model. All right, so this is how we can detect a breast cancer, which whether it is malignant or benign, using a convolutional neural network. All right, so thank you so much for watching this video. Please do not forget to like and subscribe this channel so that you can get updates directly into your inbox. Bye bye, have a nice day.